If you ask a standard neural network to simulate a swinging pendulum, it will eventually do something physically impossible. It will create energy out of nowhere, and the pendulum will swing out of control. Today, we are going to fix that using a beautiful piece of 19th century geometry called a Hamiltonian. Let's make this concrete with the simplest chaotic-looking system in physics, a swinging pendulum. Its motion is completely predictable, a differential equation any first-year physics student can write down. So the obvious machine learning approach looks reasonable on paper. Build a standard multi-layer perceptron, feed it the pendulum's current position and velocity, and train it to predict where the pendulum will be 1 instant later. Stack a few layers, add some nonlinearities, minimize the mean-squared error against real simulation data, and you have a model that, on a validation set, looks essentially perfect. Every individual prediction is close. The single-step error is tiny, a fraction of a percent. If you only ever looked at one step at a time, you would call this a success story and move on to the next dataset. But nobody just wants one step. They want a simulation, hundreds or thousands of steps, chained together, each prediction feeding into the next. And that's where the tiny error stops being tiny. Feed the network's own output back in as its next input over and over, and every small mistake doesn't cancel out, it compounds. Watch what happens to the orbit. At first it looks fine, tracing the same clean arc as the real pendulum. 10 swings in, it's drifting almost imperceptibly wide. 100 swings in, the drift is impossible to ignore. And by 1,000 steps, the trajectory has spiraled completely outward, swinging higher and wider and faster with every pass, as if the pendulum were somehow gaining energy from nowhere at all. Put a number on it. Suppose the network's single-step position error is a tiny half of 1%, genuinely excellent by any normal machine learning standard. Chain that same small error through 1,000 sequential predictions, each one built on the last, and small deviations don't just add up, they compound multiplicatively, the way a rounding error compounds through 1,000 multiplications. Depending on how that error interacts with the system's own instability, an initially microscopic 0.5% slip can snowball into a trajectory that is wrong by an order of magnitude or more, in only a few hundred steps. This is exactly why weather forecasts fall apart after 10 days, and why naive next-step prediction, applied to physics, breaks down the same way. It was never the size of any single mistake. It was always what happens when you feed a mistake back in as the next input forever. And that's exactly what's happening mathematically. A real pendulum obeys one law above all others. Total energy, kinetic plus potential, never changes. It's conserved, beat for beat, forever. The network was never told that law exists. It was only ever trained to minimize position error, one step at a time, and nothing in that objective forbids it from quietly leaking energy into the system. The bug isn't in the training data. It's in the architecture itself. To fix it, we need to go back roughly 200 years to a piece of geometry built for exactly this problem, the Hamiltonian. To see what's actually going wrong, we need to stop looking at the pendulum's swing through physical space and start looking at it through a different lens entirely: phase space. Instead of plotting where the pendulum is, its angle, swinging left and right, plot two numbers together: its position on one axis and its momentum on the other. Momentum here just means how fast it's moving, in which direction, weighted by mass. Every possible state of the pendulum, at any instant, is a single point in this two-dimensional space. And as time moves forward, that point doesn't sit still, it traces a path. Watch the physical pendulum swing, and watch its shadow trace a curve in phase space right alongside it. For a real, energy-conserving pendulum, that curve does something beautiful. It closes. Swing the pendulum, and its phase space point sweeps around and returns to exactly where it started, tracing the same closed loop, orbit after orbit, forever. Push it harder, give it more energy, and you get a bigger closed loop, nested outside the smaller one, but still closed. Give it much more energy, enough to swing all the way over the top, and the topology of the loop itself changes shape. But the pattern never breaks. Every fixed amount of energy corresponds to exactly one closed curve in phase space, and the system is locked onto that curve for as long as energy is conserved. There is a clean way to see why energy conservation forces a closed loop, and it takes only a few lines of calculus. Ask how the Hamiltonian itself changes along a trajectory, from one instant to the next. The chain rule says that rate of change equals the landscape slope in the position direction, times how fast position is changing, plus the slope in the momentum direction, times how fast momentum is changing. Substitute in Hamilton's equations for those two rates of change, and something remarkable happens. The two resulting terms are identical in size and exactly opposite in sign. They cancel perfectly, every time, for any Hamiltonian at all. The energy's rate of change along any true trajectory is therefore always precisely zero. Nothing needs to be assumed or measured. It falls directly out of the algebra, which is exactly why the curve has no choice but to close. Now put the standard neural network simulation back on the same phase space plot. Chapter 1's outward spiraling pendulum wasn't just visually messy in phase space. It's an open spiral, not a closed loop. Every orbit lands a little further out than the last one, because every orbit gains a little energy it was never supposed to have. This is the real diagnosis. A standard neural network has no reason to trace a closed curve, because nothing in its architecture even knows that closed curves are the target shape. It's approximating positions point by point, blind to the one property, a closed orbit, constant energy, that actually defines the system it's simulating. This closed-loop behavior has a name, and it goes deeper than just the shape looks nice. Physical systems like this live inside something called symplectic geometry, a branch of mathematics concerned with how volumes, or in two dimensions, areas, transform as a system evolves. Liouville's theorem makes the guarantee precise. As a patch of nearby starting conditions in phase space evolves forward in time, its shape can stretch, twist, and warp into wild contortions, but its total area never changes. Not shrinking, not growing perfectly, exactly conserved forever. That's an extraordinarily strict geometric constraint, and it turns out to be the deep reason energy conservation holds. Any simulation that doesn't respect this geometry is, quietly, cheating physics. So the real question isn't how do we make the network more accurate? It's what determines the exact shape of that closed curve in the first place, and can we force our model to trace it by construction, rather than by hoping training gets close enough? The answer comes from a single mathematical object that completely determines phase space's flow, the same object 19th century physicists used to unify all of classical mechanics. That object is called the Hamiltonian, usually written as a capital H, and its definition is almost disarmingly simple. It's just the total energy of the system, written as a function of position and momentum together. For the pendulum, that means kinetic energy, the energy of motion, depending on momentum, plus potential energy, the energy of position, depending on the angle. Add them together, and you get a single number, h, for every point in phase space. Plot that number as a height above the phase space plane, and energy becomes a landscape. A smooth surface of hills and valleys sitting over the position momentum plane, one height value for every possible state of the pendulum. Here is the extraordinary claim William Rowan Hamilton made in 1833. If you know that landscape, you know everything about how the system moves, with no further physics required. Hamilton's equations say the rate of change of position equals how steeply the energy landscape rises along the momentum direction, and the rate of change of momentum equals how steeply it falls along the position direction. In other words, both velocity and force fall directly out of the slope of a single surface. You don't need Newton's separate laws for force and motion bolted together. You need one function and its two partial derivatives, one with respect to each axis. The entire dynamics of the system is baked into the shape of a single hill. Look at that landscape for the pendulum. At the bottom, near zero position and zero momentum, there's a gentle valley, the pendulum hanging still, its natural resting energy. Move away from that valley in any direction, and the height rises smoothly, like a bowl curving upward. Near the very top of the range, where the pendulum has just enough energy to swing all the way over, the landscape develops a subtle ridge, a saddle point, sitting exactly at the unstable balance point straight up. Every feature of the pendulum's physical behavior is written directly into the geometry of this surface. That valley versus ridge geometry is not just decorative. It tells you which states are stable and which are not. Nudge the pendulum slightly while it hangs near the bottom of the valley, and the landscape slope gently pushes it back toward the low point. Small disturbances stay small, forever bounded, which is exactly the everyday experience of a pendulum at rest. Nudge it instead while perfectly balanced at the ridge, straight up, and the slope now points away from that point in every direction. The tiniest disturbance grows, and the pendulum falls one way or the other. Physicists call the valley a stable equilibrium and the ridge an unstable one, and both are visible directly in the shape of the landscape, with no separate calculation required. A trained Hamiltonian network inherits this for free. Wherever its learned landscape curves upward in every direction, it has found a stable configuration of the real system automatically. Now take Hamilton's equations and turn them into arrows. At every single point in phase space, compute the two partial derivatives, and draw a small vector pointing in the direction those derivatives specify. Do that everywhere densely, and the landscape slope generates an entire vector field covering the whole plane. A complete velocity instruction at every state the system could ever be in, for exactly which way it moves next. This is the same information as the landscape, just displayed differently. Instead of a height map, you get a flow map. And critically, this vector field isn't something you choose freely or fit to data. Once the energy landscape is fixed, the vector field is fixed too. It's forced, mathematically, by the single function h. Watch what happens when you drop a particle anywhere in this vector field and let it flow along the arrows. It doesn't wander off toward higher or lower energy. It moves exactly along the contour line, the ring of constant height, that it started on, tracing that ring forever. Because Hamilton's equations guarantee the arrows always point precisely tangent to the level curves of h, never up the slope, never down it. That's not a coincidence, and it's not an approximation. It falls straight out of the calculus. The closed loops we saw back in phase space, Chapter 2's beautiful nested orbits, are simply the contour lines of the energy landscape. Constant energy and closed orbit are the same statement, seen from two directions. You can check this tangency condition directly with numbers, not just trust the picture. At any point in phase space, compute the two partial derivatives of h, giving the vector Hamilton's equations predict. Separately, compute the gradient of h itself at that same point, the direction of steepest increase in energy. Take the dot product of those two vectors, multiplying corresponding components and adding the results. For a true Hamiltonian flow, that dot product is always exactly zero at every single point, no exceptions. The flow direction and the steepest descent direction are perpendicular, everywhere, which is precisely the geometric statement that the flow never climbs or descends the landscape, only moves along it. That one algebraic identity, checkable point by point with nothing more than multiplication and addition, is the entire proof that energy is conserved. This is roughly 200 years old. William Rowan Hamilton built this framework in the 1830s to unify and generalize Newtonian mechanics, decades before anyone imagined it might someday matter for machine learning. But look at what it actually offers: a neural network. A single scalar function whose slope automatically, geometrically, guarantees that anything following it traces a closed, energy-conserving path. If you could somehow force a neural network to learn that one function, the landscape itself, rather than the arrows, rather than the positions, conservation of energy wouldn't need to be trained into the model at all. It would be architecturally unavoidable. So here's the design question that changes everything. What if, instead of asking a neural network to predict the next position directly, we ask it to predict something totally different, not a place, but a landscape? Take that same multi-layer perceptron from Chapter 1. Keep the layers, keep the nonlinearities, keep the training data, but change exactly one thing. Instead of two output numbers, the next x and y, give it a single output, one scalar number. And instead of interpreting that number as a position, interpret it as an estimate of the total energy, h, at the input state. That's the entire architectural change. One number, reinterpreted. Here's why that tiny change is so powerful. Because h is now the network's actual output, and every operation inside a neural network is differentiable by construction, you can ask automatic differentiation, the same machinery that computes gradients for backpropagation, to hand you the network's own partial derivatives with respect to its inputs, position, and momentum, essentially for free. Those two partial derivatives are exactly the two quantities Hamilton's equations need. Feed them straight into Hamilton's equations, and you get a predicted velocity vector, where the state should move next, computed not by asking the network to guess a position, but by taking the calculus of its own energy landscape. And here is the aha moment. Because the network's motion is now defined as the gradient of a single scalar landscape, it is mathematically incapable of doing anything other than flowing along that landscape's contour lines. Exactly the geometry we spent the last 2 chapters building up to. It doesn't matter how badly the landscape itself is estimated during training. As long as the network outputs some scalar function and Hamilton's equations are applied to its gradient, the resulting flow conserves whatever quantity that scalar represents perfectly by construction. This isn't a property we hope training discovers. It isn't a regularization term nudging the loss in the right direction. It's baked into the architecture before a single gradient step of training has even happened. Energy conservation stops being a training goal and becomes a mathematical guarantee. Before going further, one clarification, because this guarantee is easy to overstate. A Hamiltonian network can absolutely still be wrong. Its learned landscape can be the wrong shape entirely. Its predicted orbits can sit at the wrong energy, the wrong radius, the wrong period. Training can fail exactly like any other neural network's training can fail. What it cannot do is fail in that one specific way. It cannot leak energy into or out of whatever landscape it happens to have learned, correct or not. Accuracy is still earned through training, same as always. Only the conservation law is free, guaranteed by the architecture, regardless of how good or bad the learned landscape turns out to be. That distinction, accuracy is learned, conservation is architectural, is the whole idea in one sentence. Look at the 2 vector fields side by side. The standard networks field from Chapter 1 is a mess, arrows pointing every which way, no global structure, nothing stopping a trajectory from spiraling outward forever. The Hamiltonian networks field is completely different. Smooth, closed, every arrow tangent to a ring, every ring nested perfectly around the last. Drop a point anywhere in it, and it can only do one thing: orbit forever on whatever contour line it started on. Same network size, same training data, one architectural constraint, and the entire failure mode simply cannot occur anymore. Of course, a random, untrained network doesn't yet know what the pendulum's true energy landscape actually looks like. Its guessed H could be wildly wrong at first, and its orbits will be closed circles in the wrong shape entirely. Getting that landscape right is still a learning problem. It just becomes a much better posed one. Instead of learning positions and hoping conservation emerges, the network now only has to learn one honest scalar function. That's the training problem we solve next. Training a Hamiltonian neural network starts, like any supervised model, with data. But notice what kind of data it actually needs. Not just positions over time, but at each sampled state, some position, some momentum, the true instantaneous rate of change of both. In practice, you get this either directly from sensors, or by taking a real trajectory and estimating its local velocity with finite differences. Each training example becomes a pair: an input state, position and momentum together, and a target vector. How position and momentum are actually changing at that exact instant, according to the real physical system. Here's the forward pass: feed the state into the network, and it produces one number, its current estimate of H. Now here's the part that makes this a genuinely different kind of neural network. Before computing any loss at all, you take the gradient of that single output number with respect to the 2 inputs, using automatic differentiation, exactly as we described in Chapter 4. That gradient is a 2-dimensional vector. Rotate it according to Hamilton's equations, swap the 2 components and flip one sign, and you get the network's predicted velocity. Its guess for how position and momentum should change right now. In practice, none of this requires exotic infrastructure. A Hamiltonian network is typically a small multi-layer perceptron. A few hundred to a few thousand parameters is often plenty for a system like this pendulum, trained with an ordinary optimizer like Atom on a few thousand sampled states. Because the physics constraint is architectural rather than statistical, these networks tend to need noticeably less data than an unconstrained model to generalize well. Since half of the learning problem, respecting conservation, was never left to the data in the first place. Training typically converges within a few thousand gradient steps on a single modest GPU, in minutes rather than hours. The double backpropagation machinery from a moment ago sounds exotic, but every major deep learning framework has supported it natively for years. In code, It is often a matter of one extra function call around the forward pass. The loss function itself is almost embarrassingly simple once you see it. Mean squared error, exactly like an ordinary regression problem, between that predicted velocity vector and the true velocity vector from the training data. No exotic penalty terms, no hand-tuned physics regularizer bolted onto the objective. The physics isn't enforced by the loss function at all. It was already enforced by the architecture, back in Chapter 4. The loss function's only job is the ordinary one. Make the predicted vector field match the observed one, point by point, as closely as possible. There is one genuinely subtle piece of machinery hiding underneath that simple description. To train this network, you need to backpropagate through a gradient. You're computing how the loss changes with respect to the network's weights, but the loss itself already depends on a derivative of the network's output. That means the training process differentiates twice, once to get the predicted velocity from H, and again to get weight updates from the loss. Modern automatic differentiation frameworks handle this cleanly through what's called double backpropagation, but it's worth pausing on. This network is trained on the derivative of its own output, not the output itself. Watch the training loop run. At initialization, the network's energy landscape is essentially noise. Its induced vector field looks nothing like the real pendulum's flow. Arrows scattered with no coherent pattern beyond the guarantee that they're still tangent to some closed contour, just the wrong one. As gradient descent proceeds, watch the predicted vector field slowly reshape itself, epoch by epoch, rotating and stretching toward the true flow. The loss curve drops steadily, the same way any ordinary regression loss would. But watch the phase space orbit alongside it. Even in the earliest, worst-trained epochs, that orbit is already a closed loop. It's just the wrong loop. Training only has to fix its size and shape, never its topology. Compare that to training the standard, Chapter 1 network on the exact same data. Its loss curve can look almost identical on paper. Similar starting error, similar convergence rate, similar final validation number. That similarity is the trap. Two models can post nearly the same training set loss and still produce wildly different long-horizon behavior, because the loss was only ever measuring one-step position error, and one-step error tells you nothing about whether energy leaks in over 1,000 compounding steps. The Hamiltonian network's advantage was never visible in the loss curve. It was built into the architecture before training began. Step back and look at what actually got learned. The Hamiltonian network was never shown the word energy. It was never told what conservation means, never given a physics textbook, never handed Hamilton's equations as ground truth to imitate directly. It only ever saw position, momentum, and the rate of change of both. The same raw ingredients any neural network gets. And yet, forced through the right architectural lens, gradient descent on ordinary mean squared error converges to something that deserves to be called physics. A single, smooth, learned energy function whose contour lines are the system's true, stable, conserved orbits. Everything so far lived in a toy, two-dimensional world. One pendulum, one position, one momentum. Real physics is rarely that forgiving. Scale this idea up to the three-body problem, three masses, like a miniature solar system, each pulling on the other two by gravity. And the phase space isn't a simple two-dimensional plane anymore. It's 18-dimensional. 3 positions and 3 momenta for each of the 3 bodies, each in 3-dimensional space. The math is uglier. Chaos becomes a genuine risk even for the true system, and there is no clean, hand-drawable landscape to sanity check against. But the underlying architecture doesn't change at all. Train a standard neural network to predict positions directly on the system, and the same failure mode from Chapter 1 reappears. Except now the consequences are dramatic instead of merely wrong. Simulate forward long enough, and small per-step errors compound exactly as they did with the pendulum. Except this time, watch what that compounding does to an orbiting planet. Around Earth, around the Sun, the orbit drifts, widens, and within roughly 1,000 simulated steps, the standard network's Earth doesn't gently spiral away. It plunges straight into the Sun, or gets flung out of the system entirely, because nothing in its training ever forbade the total gravitational energy of the system from silently draining away or spiking upward. To put a real number on it, even a modest, well-behaved numerical error in this two-body simulation can double the orbital radius in only a few hundred integration steps, And once a nearly circular orbit starts drifting outward like that, the drift accelerates, because a wider orbit samples the gravitational field differently than the one the integrator was tuned near. For a genuine three-body system, there is an extra wrinkle worth being honest about. Three mutually gravitating bodies are often chaotic even under a perfect integrator, meaning nearby starting conditions can diverge over long enough timescales regardless of the numerical method. What the Hamiltonian architecture guarantees is not immunity to that underlying chaos. It is that whatever trajectory the system does trace, correct or not, will keep obeying conservation of energy for as long as you are willing to run it. Run the identical experiment with a Hamiltonian neural network. Same data, same three bodies, same 1,000 steps, and the outcome is almost boring by comparison. The learned energy landscape, now a function over 18 dimensions instead of 2, still guarantees that gravitational energy is conserved by construction. The orbit doesn't drift, it doesn't spiral. Earth keeps orbiting the sun, stably, indefinitely, for as many steps as you're willing to simulate. 1,000, 1,000,000, it doesn't matter, because the constraint that prevents energy leakage never depended on how many dimensions the landscape lives in. Geometry doesn't care how many bodies you add. And the same trick generalizes well beyond orbital mechanics. Molecular dynamic simulations, where the energy is the potential between atoms rather than gravity, use exactly this architecture to keep long simulations physically believable over millions of time steps. Robotics researchers use Hamiltonian and closely related Lagrangian neural networks to model legged and manipulator dynamics that stay stable and controllable, instead of drifting into nonsense after a few seconds. Even certain fluid dynamics solvers borrow the same idea, replacing raw coordinate prediction with a learned conserved quantity whose gradient defines the flow. Wherever a system has something that must not be allowed to leak away, this architecture has something real to offer. There is a close sibling worth knowing about, the Lagrangian neural network, where a Hamiltonian network learns a scalar energy function of position and momentum. A Lagrangian network learns a closely related scalar function of position and velocity instead, and recovers the equations of motion through a different, related piece of classical mechanics called the Euler-Lagrange equation. The two approaches are mathematically connected. Momentum itself is defined as the derivative of the Lagrangian with respect to velocity, and each has practical trade-offs. Lagrangian networks avoid inverting a mass matrix as directly in some formulations, while Hamiltonian networks tend to compose more naturally with the symplectic, energy-preserving integrators this whole video has been building toward. Neither one is strictly better. They are two different doors into the same underlying geometric idea. Put the two vector fields on screen one last time, side by side. On the left, the standard networks field. Chaotic, directionless, no structure connecting one arrow to its neighbor, an orbit that was always going to spiral into nonsense no matter how long you trained it or how much data you fed it. On the right, the Hamiltonian networks field. Smooth, closed, every arrow exactly tangent to a ring, every ring nested perfectly inside the next, tracing forever without drifting a single pixel. Same size network, same optimizer, same training data. The only difference is a single architectural choice made before training ever began. Output a landscape, not a position, and let calculus do the rest. Hamiltonian networks are one entry point into a much larger idea in modern machine learning, sometimes called geometric deep learning. Instead of hoping a large enough model eventually discovers a symmetry or a conservation law from data alone, you build that structure directly into the architecture, so it holds by construction. Convolutional networks bake in translation symmetry. Graph neural networks bake in permutation symmetry. Hamiltonian and Lagrangian networks bake in the conservation laws of classical mechanics. In every one of these cases, the lesson is the same. A model that is forbidden from breaking a law of physics or mathematics does not need to spend any of its learning capacity discovering that law in the first place. It can spend all of that capacity getting the details right instead. That's really the deeper lesson here. Past this one architecture and this one pendulum, a neural network trained purely to minimize error has no innate respect for physics. It will happily violate conservation of energy, or momentum, or any other law you didn't explicitly build into its structure, because nothing in ordinary gradient descent forbids it. Geometry isn't a constraint you bolt onto AI after the fact. It's a design choice you make before the first weight is initialized, about what shape of function the network is even allowed to represent. Give a model the right geometric scaffolding, and the physics isn't something it has to learn at all. It's something it can no longer avoid.